Hello, I am N.K. Anand, Executive Associate Dean, Dwight Luke College of Engineering. My field is heat transfer and fluid flow. In particular, I focus my research on finite volume techniques. It is my pleasure to endorse Professor Jorge Seminario's research proposal. Professor Jorge Seminario is a professor of chemical engineering and holds Lanneter and Herb Fox professorship in the R.T. McFerrin Department of Chemical Engineering. He has published over 200 reviewed papers in scientific journals and edited 6 books in the field of computational chemistry and nanotechnology. He is the author of 2 US patents in the field of nanotechnology. Professor Seminario's research has focused on nanotechnology, working on analysis, design, and simulation of systems and materials of nanometer dimensions, especially those involved in the development of nanosensors and nanoelectronics. He recently has proposed and designed a nanosensor for the Oregon National Laboratory, now under fabrication by his research group. Thank you.
Welcome to Professor Seminario's Molecular Electronics and Nanotechnology group. The prime objective of this group is to develop new scenarios for use of molecules as electronic devices, such as programmable circuits and nanosensors. One of the most important pieces of information in nuclear field is to identify the presence of radioactive materials. Their presence, especially previous and after accidents, acts of terror, or simply the hiding of these materials for whatever purposes is of vital importance, not only to defense or nuclear authorities, but to the common citizen who needs to be protected against these substances in the same way we are protected against toxic combustion gases in our cars.
Having low-cost and small-sized sensors to detect radioactive materials in the hands of the common citizen would protect him or her and provide with critical information to guide a proper and timely response by the corresponding authorities. Unfortunately, determination of radioactive materials in the field represents an acute gap in detection capabilities.
This work seeks to develop a new handheld analytical instrument that identifies important radioactive moieties and its isotopes. The basis for the device is a plasmonic molecular sensor which is able to detect elemental radioisotopes by characteristic changes in the plasmonic properties.
This is a game-changing invention. Such extreme miniaturization for detection and sensitivity has not been possible until now. With this technology, the potential exists to perform fully portable isotopic forensics in the field or develop pixie dust sensors that can be dropped onto a suspect location and interrogated at very long distances. The plasmonic materials can have light-emitting tags for positive samples. A library can be developed to recognize these isotopes. The need for handheld devices for determination of radionuclides was identified by several national and international agencies. Specifically, there is a priority need for a portable system to provide rapid indication of the presence of radiomaterials in any environment.
We propose to design and fabricate arrays of self-assembled electronic molecular devices as sensors for radioactive materials using computational calculations and experiments. In particular, we propose to study graphene and related plasmonic materials, which are terahertz vibronics and plasmonic electronic material for molecular circuits and sensors. The idea is to use the plasmonic features in order to transfer the electrical, magnetic, vibrational, and optical characteristics of nuclear agents into the plasmon, which produces an enhancement of observable quantities.
Graphene is a carbon-based material, just 1 atom thick, but with exceptional electrical and mechanical properties. We have been developed nanosensors here on the lab that are able to detect nuclear agents with high selectivity and sensitivity.
However, for nuclear agents, we have additional possibilities due to their radiation features. Theoretical situations have shown the possible use for sensors to identify single molecules with modes in the terahertz region. This features of graphene is of strong interest for terahertz sensing and engineering. It also promises devices with high selectivity and sensitivity that will contribute to miniaturization and performance enhancement in nanotechnology, transport, and processing of signals using molecular devices.
Hello everybody, I am Jorge Seminario, a professor in the Department of Chemical Engineering. I also have appointments in the Department of Electrical Engineering and the Material Science. We want to develop a nanosensor able to detect radioactive materials. This nanosensor will be as small as a cellular phone that can be used actually by any person interested in detecting these materials. We plan to develop the science and the technology that will allow us to get a proof of concept device, and this proof of concept device will be developed using an approach that consists in the use of theoretical methods.